locus and complex numbers. So we saw a little bit of this earlier. Circles, and you may recall, we said it was z times z conjugate is equal to the radius squared. Because remember, z times z conjugate is x squared plus y squared. But now we could write it a different way, a much neater way. Because remember, locus, we're saying, what do all the points on this circle have in common? And it's their distance from the origin. Well, distance from the origin is modulus, we now know. So a much neater way of writing that is just simply the modulus of z is equal to r. Be careful with that though. Notice it's not r squared because we're saying the distance from the origin is r. But another way of thinking about it is, think of this as a vector. Any point on the circle, if I was to join it up to the origin, that would be the vector head minus tail z minus 0. We're saying the length of that vector is the radius. That's where it comes from. And of course we could shift the centre. Let's say it's W. Now previously we saw that relationship, Z minus omega, Z conjugate minus omega conjugate is the radius squared. But again, using the vector idea, it's much simpler. Here's my vector, head minus tail would be Z minus omega. So we're just saying, well, the length of that vector is R. So the modulus of Z minus omega is equal to R. We must be talking about a circle. So let's work these ones out. So if I have x squared plus y squared is equal to 16, circle, centre is the origin, radius is 4, I go, oh, well, that's just the modulus of z is equal to 4. If I put it in conjugate form, it would be z times z conjugate is 16. But tend to go with the modulus one rather than the conjugate one. This one here, well, we know it's going to be a circle because the highest power of x and y are both 2. And the coefficients are the same, but we're going to need to complete the square to work out where the centre is. So x plus 6x, well, half the coefficient of x would be 3, so x plus 3 squared. Y, half the coefficient of y is minus 2, y minus 2 squared. But of course that means we've added some constants. 3 squared's 9, 2 squared's 4, so we've added 13. So our number on the right hand side becomes 25, and there it is. Hopefully we recognise that. Circle, centre at negative 3, 2, radius 5, but if I put it in our vector notation, we're saying, well, z plus 3 minus 2i is equal to 5. So z minus the centre. So essentially, if you look at it, it's just the same numbers. So 3 being the real bit, minus 2 being the imaginary bit. In conjugate form, it would look like that. So z plus 3 minus 2i, z conjugate plus 3 plus 2i is 25. So what's the centre and the radius of this one? So if we think of it, okay, we're saying it's a vector. Whenever I join my point up to, well, it would be 5 plus I would be joining it up to. The length will be 2. So the centre is 5 plus I, or if I put it as a coordinate, 5, 1. And the radius is 2. This one's in conjugate form, so it's the first parentheses I'm really looking at. So it's z minus the centre. So the centre would be negative 4, negative 1. So negative 4, negative 1, and this one is when it's radius squared, so the radius would be 7. Of course, if you're unsure, substitute in x plus I, y for z, and then you can get the Cartesian form of the equation. Ooh, hang on. This one's not as obvious straight away. We're saying 3 times the modulus of z, because I could always factorise the 3 out. I mean, the absolute value of 3 is 3. So I could factorise that. So 3 times. So what is it saying? The distance to the point negative 2 plus I is 3 times the distance to the origin. Again, it's not immediately obvious what that is. So I might go to Cartesian form. As I say, I can factorise out the 3 to make it a little bit easier. So modulus of z, notice I've turned my 3 into a 9 because I haven't worried about putting the square root signs in. So I've sort of squared at the same time. So I get 9x squared plus 9y squared is x plus 2 squared plus y minus 1 squared. Expand all that out, it turns out it is a circle as well. So 8x squared. It's always easier to complete the square when the coefficients of x squared and y squared is 1. So let's divide everything by 8. And now it becomes a little bit easier. Half the coefficient of x, half of minus a half is minus a quarter. Half the coefficient of y, half of a quarter is an eighth. But now I've added some constants on. A quarter squared is 1/16. An 8th squared is 1/64th. How many 16s in 64? 4. So that's 5 64s I've added on all together. So 5/8 plus 5 64ths ends up being 45 64ths. So there we have it. Our centre is 1/4 minus an 1/8, and the radius would be the square root of that, so 3√5 on 8. So if you don't see it straight away, drop back into x and y's and work out what the actual equation is. Z conjugate plus 2 times z plus z conjugate. Remember, z times z conjugate, x squared plus y squared. Z plus z conjugates, well, if you add them, the imaginary parts are going to cancel, so we'll get twice the real. So I should end up with x squared plus y squared plus 4x is equal to 0. So again, let's complete the square, and it's yet another circle. Centre minus 2, 0, radius 2. So circles. Let's have a look at some lines, and we talked about a couple of lines earlier. The horizontal line, we said we could now call the imaginary part of z is equal to some constant number. That would be what all those points have in common. A vertical line would be the real part we have in common. But what if it's at an angle? Well, I'm sort of going to do this in reverse logic, because once we know it, it's obvious straight away. Might not be obvious right now. But I'm going to just label a couple of points in here. You see, any line could be the perpendicular bisector of 2 points. So I've just created 2 points here and said, well, this line's going to be the perpendicular bisector of these 2 points. Well, what's that mean? That means it doesn't matter where I place z on the red line, the distance to omega 1 will be the same as the distance omega 2. And you could prove that. So if I was to put a point here, we'd have we'd have a right angle, we'd have a side, we know they're equal, and of course we've got a common side as well. So it's actually side angle side, but we could prove that with congruent triangles. So as I say, I did that in reverse, but what that now means is if I see the modulus of, well, let's call it a linear function, z minus some number. The modulus equals the modulus, I know, hey, I'm talking about a straight line. And I know that straight line will be the perpendicular bisector of those 2 numbers, omega 1 and omega 2. So if I see this, okay, we've got talking linear function there. So modulus equals modulus, I know we're talking about a straight line. It is the perpendicular bisector of 1, 1 and minus 2, minus 1. Okay. I could do a coordinate geometry. So remember, say we've forgotten that, we don't know what it is. All right, let's go back to coordinate geometry and use our distance formula, because that's all that's really saying. The distance from z to 1, 1 is equal to the distance from z to minus 2, minus 1. So let's put it into our distance formula, expand the whole thing out, and that's going to tidy up. X squared is going to cancel, y squared is going to cancel, and we end up with the equation of a straight line. So you could always go to coordinate geometry, and I suppose there's not that much working out there. Right? It's not too bad. If you do remember it's the perpendicular bisector, you could, it's still using coordinate geometry, just different coordinate geometry. Okay, I'd need to find the midpoint, because I want to find the perpendicular bisector. So the midpoint of those is minus 1/2, 0. I'll find the slope of the line joining those 2 points. That's 2/3, but we want the perpendicular to that. So the slope we want is minus 3 on 2. Point slope formula, and eventually when we tidy it all up, yes, we get the same answer. And you might say, well, hang on, the first way actually seems to be a lot easier, a lot simpler. And maybe it is for that particular one. Sometimes the other one's going to be easier. Like, if I've got a question like this, I'm not going to waste time finding the equation, because they never actually asked for it. They simply said, just sketch it. So if I know it's the perpendicular bisector, I can go, oh, okay. Well, it's going to be the perpendicular bisector of 4 and -2. Halfway between 4 and -2, oh, well, that's 1. Perpendicular bisector, there's my sketch. Mind you, now that I see the sketch, the actual equation is quite easy because it's just a horizontal line. What's that going to be? It's just be y equals 1, or if you prefer, the imaginary part of z is equal to 1. Rays. Oh, what's a ray? Cast your mind back to probably year 7. We did all those formal definitions, the difference between a line and an interval and a ray. What's a ray?
A line with an edge.
That's an interesting way of defining it, because a line, of course, is something that has no endpoints. But I get what you're saying. So in a way, yes. Right, so a line obviously goes on forever and ever in both directions. An interval has a definite starting and finishing point, and the ray is the one that's in between the two. It has a starting point, but no definite finishing point. So that's what we're talking about. So something like that. And that we can define using the argument, because all of the points on that particular ray would have the same argument. They're all making the same angle with the x-axis. So that could be defined as simply, well, the argument of z, any point on that line z, or that ray z, is equal to theta. And if we were to shift the starting point of that, well, let's call it a vector, it is what it is, then we would say, well, okay, the argument of head minus tail, z minus omega, is equal to theta. Notice the starting point I've circled, and that's because the starting point can't have an argument. If you haven't moved off in any direction yet, well, how do you know what the angle is? So you always circle the starting point for these ones. That brings us to questions like regions in the plane, like we saw with coordinate geometry. But we can do it a different way now. We want all the complex numbers such that its modulus is less than 1, and its argument is in between 0 and pi on 4. Okay, let's do it a bit at a time. If the modulus is less than 1, well, the boundary would be the modulus is equal to 1. And so that's going to be our circle, radius 1, centre at the origin. And you'll notice I've dotted it because it's less than. But now we only want, it's not completely inside that circle. We only want the ones where the argument is in between 0 and pi on 4. Well, an argument of pi on 4, it would go off at an angle of 45 degrees, pi on 4, and 0 would be the x-axis, so in between those two. So we'd be in that little sector there. A couple of technicalities on this. I should circle those points of intersection, just like when we saw regions in the plane. If you have a not equal to as part of the boundary, then the point of intersection can't be part of it either. And I suppose technically I should be dotting those rays once I go past those. Just be hard to do that in PowerPoint, but that's technically I should be doing that. We're going to sketch the modulus of z plus 2 minus 2i is equal to 2. Well, again, we've got a circle, but its centre has been moved to negative 2, 2. Now this is where it's really important we're accurate, because you'll notice the point of the centre is negative 2, 2, and the radius is 2 as well. So when we draw this, it should be touching the axes. So if you don't draw it accurately, you might have your circle cutting the y-axis or the x-axis. But if the radius is 2, it should just be touching. So there's our circle. Find all the possible values for the argument of z. So every single point on that circle, what would the arguments move in between? Work that out. It's got to go between the two tangents to the circle, which conveniently for us happens to be the x and the y axis. So I haven't got a lot of work to do to work that out. But if it was somewhere else, that's how you'd do it. You'd draw in your tangents to the circle, and you have to calculate the angle that those tangents make. So for my one here, nice and easy, it goes in between pi and 2 and pi. Find the minimum and maximum values. Where would the minimum be? Where would the maximum be? Of course, the easy answer is on the circle, because all the points are on the circle. But again, we're saying if I join z to the origin, I want to know what the biggest one will be. I want to know what the smallest one will be. And that will happen when you join it through the centre of the circle. Okay, so the blue vector there would be the biggest it could possibly be. The black one there would be the smallest it could possibly be. All right, now what we're going to do is work out those lengths. What do we know? We know the radius of the circle is 2. What else? We could work out the length from the origin to the centre, couldn't we? Bit of Pythagoras. Using my ratio 1, 1, root 2, but in this case it's 2, 2, 2 root 2. So distance to the centre is 2 root 2. So therefore, when I add on the radius, the first one I did is I subtracted the radius. So the minimum would be 2 root 2 minus the radius, and the maximum would be 2 root 2 plus the radius. Okay.